Hello everyone. Today we shall be learning to simulate the epic journey of our Earth around the Sun using only Newton's equations. If you have yourself and your laptop to get coding, we are all good to get started. Remember, this video is absolutely beginner friendly and anyone can get this set up by only watching this video. So without any further delay, let's dive right in. I shall begin by briefly showing you what your final result will look like. What you see on the screen is the Earth and the Sun. We have accelerated the simulation so we can see the Earth move and the Earth orbits the Sun precisely how it should. We assume in the simulation that the Earth and the Sun are the only two bodies and that only they can have gravitational influence. In later videos, for those who have subscribed, we shall also try run a three-body simulation and see how small changes in parameters can have distinct results, and also try placing some other planets in our solar system. But for this video, let's get started with the code. Right, so let's start with the code. First we start by importing the necessary libraries, and we'll only use two libraries in this code, and that is going to be numpy and matplotlib, with numpy being to compute values such as cos and sine, and matplotlib to plot what we have. If you did not install the libraries yet, just open Windows PowerShell or as a Mac terminal and run pip install the library name. In this case, pip install numpy and pip install matplotlib. I'll just start writing the import code. P import matplotlib as plp, and we're also going to use func animation module from matplotlib, which is going to actually help us animate the objects like what you saw in this case as the Earth moving around the Sun. So from matplotlib import func animation. Perfect. Now that we are done by importing the libraries, we can start with the constants. So hashtag constants. First of all is the universal gravitation constant, that's 6.67 into 10 to the power minus 11. E here sort of represents 10 to the power, so it's 10 to the power minus 11. The mass of the Sun for a fact is 2 into 10 to the power 30. The mass of the Earth is 5.972 into 10 to the power 24. The radius between the Earth and the Sun, or simply the distance between the Earth and the Sun, is 149.6 million, and million as well known has 6 zeros, so 149 into 10 to the power 6. And the time is basically the time for a revolution in seconds. That's going to be 365.25 because a year has 365 days and a quarter of a day, multiplied by 24, that's the hours, multiplied by 60, that's the minute, and multiplied by 60, that will give us the time in seconds. Now that we're done with all the constants, we can start with the equations. And first up we have the universal gravitation equation, which is basically an equation that helps us understand the force of gravity between two objects. The equation states that Fg, or the force of gravity, is equal to gm1 m2 divided by r square, where m1 and m2 are the masses of two objects, r is the distance between them, and g is the universal gravitation constant. We have already defined that up, so we may start. F is equal to g times mass of Sun times mass of Earth divided by r square. Perfect. Next up we have the orbital velocity. The orbital velocity v is equal to the root of the gravitation constant multiplied by the mass of the Sun in this case, the whole thing divided by the distance between them. So let's just type that down. V is equal to np, the sqrt, which is just square root of the gravitation constant, which is mentioned above, the mass of the Sun, the whole thing divided by r, which is the distance between them. The orbital velocity is now done. Let's proceed to the next one. Right, next we have acceleration, or specifically centripetal acceleration, and centripetal acceleration is simply equal to v square upon r, so we can just put that in. and we also have angular velocity or omega, which is equal to 2 pi. Pi is something we can get from numpy upon t. So the angular velocity is equal to 2 pi upon t, acceleration is equal to v square upon r. This means we have completed with all our basic equations. Time to head to all our constructed functions. So I'm just gonna create another section here. Perfect. First of all, small t, which stands for the time in seconds, which is gonna tick, is equal to np dot linspace 1 t 1000. So what this basically does is that it creates 1000 equal intervals of this time, which can be run in each frame. And why 1000? Because it is a good balance of efficiency and accuracy. Now let's start with the position functions. So for the position functions, we have x is equal to r times np dot cos omega times t, because the x function with respect to time t is equivalent to r, the distance, multiplied by cos omega t, which is basically what we have done here. Y is equal to r times np dot sine, obviously, times omega times t, which are both the position functions. Just gonna save this before proceeding further. Alright. Next up, we have the velocity functions. Perfect. The velocity in the x direction, or the x component of the velocity, is equal to negative r omega square times np dot sine omega times t. Right. This is for the x component of the velocity, and the following is the y component for the velocity. And then we are left with the acceleration functions. One key thing to note throughout is that this is in a 2D plane, so we are considering only the x and y components throughout. Alright, so acceleration in the x direction is equal to negative r omega times omega square, not cube, square, times np dot cos omega times t, and acceleration in the y direction is equal to negative r omega square times np dot sine omega times t. Yeah, perfect. I'm just going to save this again. Right, next step, we have perhaps the most crucial step of all of this, and that is going to be plotting. Let's start. Fig x is equal to plt or matplotlib dot subplots. Fig size is going to be 8,8. So this essentially sets a new window or of matplotlib that sets a particular figure size. Then we have ax dot set x limit, and that is going to be negative 1.5 times r to positive 1.5 times r. And we want to set the same y limit. Yep. And the reason why we are setting both axes to have the same limits is because we essentially want our figures of the sun and the earth to like circle and not elliptical or any other shape as such. Because for example, having a different x limit and y limit could stretch out the circle or even the graph, which is something we don't want. Now I'm going to say ax dot set aspect equal adjustable is equal to box. Perfect. We're done with the key plotting aspects. Now we're going to go for plotting the sun and plotting the earth. Alright, so first stop is plotting the sun. So for plotting the sun, I'm going to be creating another section. Hashtag plotting the sun. Sun is equal to ax the plot. Okay, this is the basic thing what we want. I'm just going to set both of these to be 0 and 0. 0, 0. Mark a size, let's say 20 instead of 10, because we also want the earth, which is going to be of a smaller marker size. What this basically does is sun as a yellow point bigger than the earth, and you'll know why just in a moment. Earth is equal to ax. I'm actually going to copy this. Dot plot. I'm just going to change this to BO since we want it to be blue, and marker size to be 10, which is going to create earth half the size of the sun. Of course that's not real, but for our case we can imagine it that way. Anyways, it doesn't affect the motion of any of the planets or the celestial bodies. Alright, now that we have the earth and the sun at their initial positions where they should begin, we need a function that would update the position of the earth with respect to the change in time, or change in frame in this case. So I'm just gonna go down and I'm gonna say function to update the position of the earth. Alright, so I'm just gonna name the function update frame. That it's gonna only take the argument frame. Earth dot set data. Okay, this works. X frame and Y frame, and we want to just return the earth. Perfect. Next up, we want to create the animation, and it's not going to be very hard. All you have to do is func animation. We are going to be using this module what we imported earlier. Fig update, because we want to be updating it. Frames is equal to len t. Interval is equal to 20, and blit is equal to 2. Perfect. This is almost it. For the last part, we are just going to be playing with the labels and titles and stuff. So I'm just going to say text labels. So first of all, we are going to add the axis labels. The x-axis label, I'm just going to say x position. You can name it whatever you want. The y-axis label, I'm going to name it y position. The title of the graph is going to be orbit of earth to sun, and we want the grids. You can put it to false, though you'll not see the grids which you saw in during the beginning of the video. And finally, we want to be presenting the graph, or just show it. So I'm just going to say plt.show. That's it of the code, and that's how it works. Alright, next up, you want to be going to your folder where your recording is and typing cmd and hitting the enter button. Then you should have Windows PowerShell open. Next, type py-driver.py in my case, or whatever file.py in your case. Okay, there's an import error. No issues. Let's go back to our file. Alright, so let's see what is the case. Okay, first of all, T capital here. Next, it's an import error, so alright, here's the error. Actually, matplotlib.animation in this case, and .pyplot in this case. That's it. Alright, if you repeat the same steps again, we arrive at Windows PowerShell. I'm gonna try running the same file again, hopefully with no errors. Alright, we have successfully run the code, and we see that the sun is in the center, the earth is orbiting the sun. So congratulations, we have run the code. Now it is running this space at this space. The earth is orbiting the sun at this space because we have actually in our code used 1000 in the linspace. We can update this to the real time which is this much. This value is basically the product of these. And if I save it and I'm gonna run this again, perfect. This is the original place, and it seems that it's not working, but if we have a closer view, a very close view, we can see that in reality the earth is moving at a good pace. Thank you for tuning into this video, and I hope this video was educational and interesting for you. If you like this video, please support me by sharing this video and subscribing to the channel. Bye, and catch you in the next video.